Okay.
Thank you.
Okay, so you can see here that this is a very simple model that has just 4 reactions and essentially just 3 species. So let's look at this model and try to understand what will happen. So the first reaction that I selected here is a reaction with no substrate, just a product. So it is a source for the species called R. And as you can see, the term is a constant multiplied by the concentration of this other species called S. So this is essentially the most simplistic way of having a stimulus called S upregulate the level of a gene or protein called R. Okay. Now, this protein of interest called R also has another reaction, this time with no product. There's just a substrate, but no product, which is degradation of R. Again, this is something extremely simple and typical for many biological models. And if we look at the rate of this reaction, it is a forward rate constant on the multiplied by the concentration of R. So your typical mass action kinetics. The higher the concentration, the faster the rate of degradation. But the forward rate of this mass action kinetics is not a constant, but something that can vary during the simulation. So this simple expression essentially shows you that the rate of degradation has some baseline rate given by this 0.1. And then if there exists another species E, that species actually inhibits R by stimulating its degradation. So E inhibits R or downregulates R by increasing the rate of degradation. So here we have R is being upregulated by S and downregulated by E. Now this E protein participates in 2 other reactions because it can have a phosphorylated and an unphosphorylated state. So the phosphorylation reaction is a Michaelis-Menten. The dephosphorylation reaction is a Michaelis-Menten. And the hypothesis here is that only the dephosphorylated form will actually stimulate degradation of R. The phosphorylated form does not do that. And to close the loop, the phosphorylation reaction itself is being stimulated by, it has a Vmax that depends on the concentration of R, right? So any guesses what will happen in this model if we run a simulation? What would be the behavior of this model? Anybody?
Someone says
okay, it would be dependent on the initial conditions. And let's put in some initial conditions. Now let's create an application and specifications. And let's say that all of E is unphosphorylated at the beginning, and there is no R, but we can produce that by having. So what if the initial conditions are like this? What will happen?
Would it just stay unphosphorylated for the whole time?
It will stay unphosphorylated because R will never be produced because S is 0, and the rate of phosphorylation and dephosphorylation depends on S, but not at that level. So it will actually find an equilibrium. So let's say this, let's run it. And this is 10, this is 0, and it will not change because unlike the production of R, where we have the degradation of R, where we put in a baseline level, in the phosphorylation reaction, we did not put a baseline level. So if R is not present, there's absolutely no phosphorylation. So R is a required catalyst. There's no baseline level. However, if we would have done this R plus 0.1, then there would be some level, some baseline level of phosphorylation. But since we did not put any baseline level of phosphorylation, they stay like this. Now, if we actually put in a stimulus present here to produce some R, then things will happen, right? And there will be E and EP and S present. Okay, so E and EP. And it will take a while. It's very little here. And we can run this for a longer time period. Oops, that's a problem with my Windows 10 machine. And you just okay. Okay, so E and EP, there will be very little phosphorylation at that level. And as you might guess, if we have more and more S, we increase the stimulus, there will be more phosphorylation and it will settle at a different level. So let's test this out. Let's do simulation, and we want the value of S, which is this one, the initial value of the stimulus, to do between Now, I have not yet tested the parallel run of parameter scans on my new Windows 10 machine, which has some issues, and we'll see if it actually did run them all 11 within an instant, which is a very good sign. So at 0, at 10, at 20, at 30, at 40. So you can view these like this. So as you can see here, there is a behavior where it suddenly, at some point where stimulus goes above a certain level, it will quickly run and reach an equilibrium with almost everything on the other side in the phosphorylated form. So one of the main things that you may want to do during your model is change what happens during the run of a simulation. So let's try and actually see if we can increase the stimulus at a given time point. How would we do that? Well, what we can do is under protocols, we can introduce an event. And let's say at what time? Let's say in a linear time range between 10 and 100, 10 values. And this, it's just a trigger condition, which you can trigger the event by many different things. So here I just chosen a fixed time series, but you can do when any condition becomes true. So for example, if the concentration of some species of interest goes above a certain threshold, then you trigger something sudden to happen where you can alter the way the system works. So as you can see, just from the predefined trigger conditions, you can use this in many different ways. You can also plot the trigger, which what it does is just creates the Boolean functions for you and say, let's say over the course of 200 seconds, what will happen? Well, you know, I chose a simple trigger. At every 10 seconds, it will trigger up to this point and then no longer. Okay, so we know when the events happen, but what should we do when these events happen? You just add an action. And I can modify the value of any species or any global parameter. So let's say S, I'm going to modify S, and I will say okay, and what should it be? Well, maybe I can just, I want to increment it, and you can do things like S+1. So whatever the value of S is at the time of the trigger, it will go to, it will increment that value by 1 micromolar. And now we can see what happens. And we can do a simple simulation. That will go for 200 seconds. Yeah. Right. To do this again because of that display issue. No. Okay. So the initial value of the stimulus was 1. So the phosphorylated form of EP, it settled to an equilibrium, which is reached fairly quickly. And then a new equilibrium, a new equilibrium, a new equilibrium going on like this. Now, if we do this, we notice here that there's some step increases. And let's try to see how far up we can go with the stimulus. So since it only takes about a second to equilibrate, oops, sorry. We can have the trigger fire more often and run everything for a longer time period. And edit this. Let's go for 1,000 seconds. The values.
So Jan, there's a question in the chat you might want to take a peek at about whether you can trigger on steady.
Yeah, I don't see that is the way to set a trigger condition when the system reaches steady state. Well, it depends on what the definition of steady state is. The problem for that, like, you can probably define this as the rate of change of a particular variable being lower than some arbitrary threshold. So you can compute that rate of change and set your threshold and use that as a trigger. And say, okay, and
but as we've said all along, it's always better to, if you're doing a stimulus, it's always better to be sure that the system is at steady state before you start your simulation. And we showed you, there were a couple of demonstrations this morning about how to do that. If anyone wants to see that again, it's an important enough issue that we'd be happy to show you that again.
Okay, so this will take a little bit longer. Maybe let me cancel this and change it so that things are a little bit faster. So let's say don't have to let it settle at equilibrium for that long. So that should be faster. So while this is running, Theo followed up in the chat about parameter estimation.
Yeah, I'm answering that. It's actually a common problem to try and have a parameter estimation force an intervention to happen at steady state. And the way to do that is, well, there's several ways to do that, but the one that has worked in practically more often is that you set up the time course to have a long time course, and your initial, what you have as initial conditions, you apply them as an event, and you have to have that time between the beginning and the event to be long enough that the system relaxes to the steady state. It's not the, in theory, it's not the best way to do this, but in practice ends up being the best way to do that. So we've done that in one of our models. We set the, even though what we were trying to estimate was a time course of 100 seconds, or in this case, sorry, 20 days, we ran a simulation that worked for 100 days, and then the stimulus, that is what we want to fit, is only applied at day 200 and then goes to 220. So we have the first 200 days allows the system to relax to a steady state, even in different parameter conditions. Now, in some extreme values of the parameters, 200 might not be enough. So that's the one thing you have to be careful, and it's not easy to figure out, basically.
Yeah, there's generally also in Copasi the option to start a time course in steady state.
Yeah, but then if it fails to find the steady state,
that situation. But if the parameters that you are picking, there might be no steady state.
yeah, that's the problem, and then you get infinities and the thing stops. So what I mentioned is in practice better, even though in theory might not be the ideal.
Okay, so to avoid the display issues and rerunning it, I just ran it on the server. So the actual plot results data are being saved, and see. Let's see how this one works locally. Okay. So, and this one also completed. So we go back. And retrieve the results for R, E, EP, R, and S. So obviously we incremented our stimulus. This changed from mostly unphosphorylated at some point when the stimulus reached a different level. It really came down hard to an unphosphorylated, to the phosphorylated level. So what you can see here is a kind of bistable behavior. Up to a certain level of the stimulus, the E stays in mostly in one state, and then it switches to almost completely in another state. Now, if you fine-tune the parameters a little bit more, which is what I did in this other saved example, you can make this behavior be less dramatic or more dramatic. And let me go back to the other window, which is this one, where you can see E and leaves a little bit of space here and then comes back up. So what's different here? In this particular model that I had already done, I had introduced a second event. So what I did, incrementing the stimulus up to a certain level, and then decided to come back and decrement the stimulus. So let's see if we notice something special about this. So when we increased slowly the stimulus, it stayed mostly unphosphorylated for quite a long time, up till about more than 1,000 seconds, when it suddenly went to the other equilibrium level. So it took a fairly good increase. So at this point, the stimulus, so we were at a little bit over 1,000, so was maybe 1.6, 1.7 when the more dramatic shift to the other ratio of equilibrium happened. However, when we came down with the stimulus, now it stayed quite a bit longer in the upper equilibrium state until it decided to come back down. So coming back to fairly low level of phosphorylation happened again well past the halfway point of reducing the stimulus. So at different levels. To best illustrate this is you can, plot things not only as time dependent, but you can plot one variable as a function of another variable for the different time points. So this is the stimulus, this is the response. And you can see how R here suddenly increased to that level and came back down at the much lower level of stimulus. So if you would plot E versus EP, R versus S versus the stimulus. So E as a function of the stimulus level, you will see this phase plot, which is called, that shows hysteresis. So there's a certain level of stimulus that's required to trigger the massive phosphorylation when you go up, and then you have to come well below that threshold to fall back. So this is like a toggle button behavior where you need to go at much higher levels of the stimulus to move to shift to the other equilibrium behavior, and to much lower in order to come back. So this is a pretty nice example of how a simple set of 3 interconnected reactions can create a behavior that is doing a bistable switch. To exemplify the events a little more, I'll just show you yet another way to do things in this other window. the first event for the first 1800 seconds to go up, you can do conditions like this. This is just for fun, done that way, where you can have some periodic function that oscillates, and you can figure it out when it becomes true. So the basic take-home messages are that you can specify any number of events in an application, and every event can have its own trigger function that can be arbitrary, predefined, or dependent on the variables in the system during the simulation. And every trigger can do one or more actions where you can modify the value of any global parameter and any species. So if you want to change a rate in a local parameter in a reaction, you will have to make that local parameter dependent on a global parameter in order to use the event. So the one thing that's inaccessible to events are local parameters. So species and global parameters. And now I'm going to move to scripting and running things online in an HPC environment. But first, let's see any questions regarding events.
Just a reminder to people that events can be added both in Virtual Cell and Copasi. I had also showed how to add events in the earlier presentation. So both of them can allow you to do this in fairly similar ways.
Okay, Pinar is asking, and that's actually true for most tools that support the SPML standard. And the events are assigned per application basis, not per simulation. So all simulations that are defined in the same application will inherit the same events, but you can obviously have copy the application to another application, and there you can run the simulations with different events.